Fatigue analysis of UHPFRC steel composite bridge deck, considering self-healing behavior and fatigue line shortening of rank UHPFRC under surface water conditions. This is the content of these presentations. Introduction. The ultra-high performance fiber reinforced concrete UHPFRC with outstanding properties such as the high strength, strain hardening behaviors has been used as reinforcing overlays for orthotropic steel bridge deck to improve the fatigue performance of this kind of structure. Under water conditions, UHPFRC has high self-healing ability, represented by the high percentage of the rock closure in UHPFRC specimen. However, under fatigue loading, the reduction of the fatigue line of concrete material under water conditions has been reported in this study. The objective of this research is to develop an analytical models based on the finite element methods to investigate the fatigue behaviors of UHPFRC steel composite deck subjected to moving wheel loading under surface water conditions. The same healing behavior and reduction of the fatigue line are considered in material model of rank UHPFRC. The analysis will be verified with the experiment from Scientific Construction Association. Material model of UHPFRC. After the first day under right conditions, water has been supplied on top surface of the overlay for 1 night before stage 2 of fatigue test. Some phases for material model of UHPFRC in the fatigue analysis of stage 2. Phase 1, self-healing of UHPFRC for 1 night under surface water conditions. Phase 2, a higher degradation speed of UHPFRC under combined actions of fatigue wheel loading and surface water conditions. The stress-strain relationship of UHPFRC are shown in these figures, which is decomposed into non-rock component and rock component. For the phase 1 of material model, the self-healing of UHPFRC in terms of increasing in the reloading stiffness and tensile strength under surface water conditions are considered in the fatigue analysis. And the recovery ratio are chosen as 70% in this current model. For phase 2 of material model, it is assumed that at 2 million cycle, the stress level in water conditions is chosen as 70% of that from right conditions. And the breathing stress relations applied for the rock UHPFRC under surface water condition in the stage 2 can be calculated as so in this equation. Analytical model of UHPFRC steel composite deck. The FEM model of the composite deck is shown in this figure. 7 load locations are assigned along the loading lane with the load level of 100 kN. The non-uniformly distribution of the wheel load along the transverse direction and longitudinal direction are assigned for the tire contact area as shown in this figure. Fatigue degradation model for UHPFRC steel interface. The total expansion of 28 mm in transverse directions of the delamination areas at the interface is applied in stage 2, and it gives the same expansion speed from the reverse state under right conditions. Result and discussion. This figure shows the transverse strain range result at the strain gauge SL1 in steel deck plate. In stage 1, due to the occurrence and expansion of the delamination area at the UHPFRC steel interface, the significantly increase in transverse strain range can be observed. So in this figure. And after that, in stage 2, under surface water conditions, due to the recovery in reloading stiffness and tensile strength caused by the self-healing of UHPFRC, the decrease in strain range level obtained at the beginning of stage 2. After that, under moving wheel loading, due to the fatigue line reductions of UHPFRC, the increasing tendency of downward strain rate at this location can be observed. In this phase 2 of material model of UHPFRC, by applying a higher speed of rigid stress degradation in UHPFRC, an acceptable treatment in tendency from analytical and experimental strain rate result could be obtained, especially for the early cycle of this stage. This figure shows the maximum reachable strain distribution on the top surface of UHPFRC overlay S1A. The rough regions are shown by a pen from blue to red color. In phase 1, due to the self-healing of UHPFRC rock, the maximum reachable strain value decreased, as shown in this figure. And then, under moving wheel loading, due to the reductions of the fatigue life of UHPFRC, the increase in maximum reachable strain level could be obtained throughout phase 2, as shown in this figure. Conclusion. The 3D FEM models were performed to investigate the fatigue behavior of UHPFRC steel composite bridge deck subjected to moving wheel loading under surface water conditions. Due to the self-healing of the fire crack in the UHPFRC overlay, the mechanical recovery of reloading stiffness and tensile strength from the cracks are obtained. Later, under moving wheel loading, by considering a higher speed of the bridge strength degradation in rough UHPFRC, the analytical strength range result of the steel deck plate exhibit an acceptable enrichment in tendency in comparison to those from experiment.